the presenters please send to the list, but I think no one sent, so, yeah. So the presentations belong to the presenters, so we cannot send on their behalf, so we ask them to send. This is my slide, yeah. I mean,
Did you send those to them?
that I didn't send, but I can send it, no problem, yeah. Our slides are okay, they're public, yeah.
I just want to be lazy and copy.
No, don't copy anything. Just listen, yeah. Okay, I guess we're going to start. But we are still missing 2 presenters. It's a little funny. Okay, folks, time is up. Now, this is a 5GAN and GIP mailing list. I send you a couple of times what that means, but I forget myself too. IP is basically IP aspects of 5G. And we have been having these meetings a couple of times in the past. So this is, I think, 2nd or 3rd meeting. Now, one thing I would like to say is, again, very quickly, we have this invited presentation type of, the meeting. But we would like to shift more and more towards IETF style meeting, that is discussion of the drafts. So we would like to encourage people to write drafts and have discussions and then discuss them. And that is going to help us in the future, for future steps like going for a BOF and so on, to judge if this activity is getting into some maturity. Okay, oh, here's Tom. Okay, we are missing Michael only. I'm sure because his is last, no problem. So, okay, Scribe, Dave Allen agreed to be the Scribe. Thanks, Dave. Now we start then with Professor Vitek's presentation. So we got to connect to the, need to,
don't need to screw for contact.
Okay, I'll do this one. He's going to present from his laptop because he has a special presentation.
Okay, I think we don't need
I have this 2-minute mark here. I'll indicate the time to the
I will just
presenter.
talk until the 2-minute sign.
And we're going to be very brutal, okay? Just cut 10 minutes.
Good. So welcome everybody. As the chair already said, my name is Frank Fitzek. I'm working at the TU Dresden at the Deutsche Telekom chair, as you can see, for communication networks, and together with Gerhard Fettweis, I'm leading the 5G Lab Germany. And I was asked now to give a little bit of introduction about the 5G stuff, what it all is, and how it links to already ongoing activities here at IETF. So one thing that we always tell the people is 5G is different to other technologies like 4G and 3G, because now we already know the use cases of 5G. And we can already see where the money will come from. And from the use cases, what you can derive very quickly are these technical requirements, right? And I think most people understood, oh, there will be more bandwidth, like 10 gigabit per second per user. But what there will also be is this kind of latency. So you have to have latency maybe many times in context of web pages, latency in Facebook and Google, Amazon, how they want to reduce the latency. But this latency is even more because we are talking about this 1 millisecond delay. Others might say 2 or 3. And we at the 5G at Germany always refer to 1 millisecond because what we want to do is later we want to control and steer cyber physical systems. And when you want to do that, besides latency and data rate, you also need security and reliability. The bad news is when you think about these things, how to get 10 gigabit per second, 1 milliseconds, each parameter per se is already difficult to achieve, but you have to get them at the same time, right? And this is what it's all about. And what we are thinking about 5G is not only that you have to think about the air interface, right? What is very important is the network and the cloud, and mainly this is 5G because this one is just an add-on. But the silicon is also something that we are looking in for providing security mechanisms and have to have something like fast computing. This is the 4 tracks that we have identified at the 5G Lab Germany, and I will just motivate a few of them. So when you think about 5G and you look into the context of from 1G to 5G, then what you can really say is that everything that was before 5G was something connecting people, right? You remember the Finnish company that always said connecting people? That was about 10 billion human beings that wanted to communicate with each other, always servers, YouTube, Facebook, Live, right? And if you talk about 5G, we talk about 500 billion things that we want to control, right? And this is already different. And controlling, this is ubiquitous communication, this is ubiquitous control and scale. But you also have to support the 7-10 billion people over here, that's clear, but that's not the main thing and not really the tricky part in the game. So if you do that, we often talk about the tactile internet. So an internet that gives you feedback in a certain time, and this is the 1 millisecond. If you now think about what is the ping time nowadays, if you go to 4G, you have something like 30 milliseconds, but this is just the ping time on layer 2. So if you invoke the cloud, you will see higher values there. What we think about is a 1 millisecond end-to-end delay. And where do we get that, right? We talk with a lot of standardization bodies about this. IETF is one of them, IEEE, ETSI, and all of them talk about the tactile internet. And 5G is the first network that really supports this kind of tactile internet in the end domain. And if you talk, sorry, about latency, this is a picture I very like. You see some gamers there. They always knew that latency is more important than data rate, right? And the nice thing is they also give you the explanation how to get low latency. You just gather together. So proximity is something that brings you low latency. Unfortunately, I cannot show you this video here. It's not starting on the machine, but it's something that we built up some years ago. It's just something like an Oculus Rift where you have a camera on top of that. And what you do is you just see what the camera sees. It's a normal one-to-one copy of the real world. But what we can do then is to adjust the latency. It's very funny to see people trying to catch a ball with 15 milliseconds extra delay. Right? It's nearly impossible. Right? If you want to try it out, we also did it as a cardboard application nowadays. You can just download it and just try it out yourself. So if you then think about what is this 5G kind of use cases, I mean, steering something like humanoid robots is something interested very much for us. If you think about this industry 4.0, as they call it here in Germany, or industrial internet, if you think about something like robots, nowadays they are standing still, they have one program and they're just running that. In the future, these robots will interact with each other. And then you need the 1 millisecond. If you talk to KUKA, who is building these robots, they will say 1 millisecond is the maximum there now. They would like to go lower than that. And then, of course, you have something like this kind of drones flying in the air, not only using this network to control these drones. A lot of people think about Amazon just bringing my next new gadget, but here it's all about these things that are building the network. It's not only that they're using it, they can also build it, right? It's not only the drones, could be cars. There's something like smart grids when you want to control different kind of energy grids, and if you want to bring them together, you know that you have to look at the phases they have. You have 50 hertz at the energy grids. If you want to put them together, 1 millisecond is already 18 degrees of phase. So if you have 10 milliseconds, this is a shortcut. Well, we can live with reactive power, but shortcuts is not what we really want. Also interesting, these were the first people coming to us to say, and when they heard about the 1 millisecond, they said, hey, you have a network for 1 millisecond, we need this. So the farmers out in the field, they want 1 millisecond. And my joke in this place is always to say, if the farmers get it, that we want 1 millisecond, the rest also will understand. Okay?
Yeah, why farmers do?
And I'm going to just explain that that has to do with the control of the machines to each other, right? This is something and where they have to be very precise. And the other thing is they want to really to be precisely on the ground. So the soil is very important, and they don't want to go a little bit left, a little bit right after year after year. They really want to have localization, and they do localization via communication points. One of the things that I did not name here, I just make a little bit more emphasize on this, because we are here in Germany and we deal a lot with car manufacturers, is about already control that you have in the car. Currently, you have control between the wheels, and this is already 1 millisecond or 2 milliseconds, depending on the where you buy it. If you have a Bosch system, it will be 1 millisecond where the wheels communicate to realize something like ESC or ABS. But in the future, what we want is we want to have platoons, right? And if you have platoons, then it's not only single car, but you have to communicate with all the wheels. You really want to bring them together, 200 kilometers per hour, like 50 centimeters car after car. There has to be really precise communication. And the more things you get into your queue, the more complicated it becomes. So the one question is, why do we really need communication? Why don't you can just do autonomous cars, right? Autonomous is for me cars that are just relying on their own sensors.
2 minutes.
I will read them. So
Okay.
what you see here, these are some robots, and these robots are just following the line. And then they have a distance measurement to understand what is in front of them. And what you see is they're doing a pretty good job, right? And they do it as long as there's no disruption, right? We just have to wait, even if my 2 minutes are running. Now you see there's a disruption coming in the end, and the first one will stop, and then you will see the second will stop, and the third one will stop nicely, and the fourth one, and after the fourth one, you get a little bit of chaos. This is control theory. If you combine linear systems of second order, and you go to order number 8, then you have a problem, right? So therefore, we need some kind of communication. And what we want to have is something like this system, right? If you have a network and the cars can communicate directly, but you also would like to have a communication where you go directly to this kind of streets, and what you see is you want to have something like this. You have a network that can steer the cars into the intersection. And this network, what it will do is it will combine all the sensors of all cars together, and you make better decisions. Remember the Tesla problem? It was looking for a truck. It did not see the truck. If you just would know that there is a truck. So just to tell you that we have built something like this, if you want the videos, they're on the 5G Lab Germany DE webpage. We built such a system where you have 8 cars. They still have autonomous sensors, but they are also via a network share these this kind with each other. And you see the intersection here, right?
10 minutes. Sorry, I have to cut. We have to cut.
Okay. And let me just show you the last. If you don't want to hear that, then I said just. Let me give you the last slide.
Let's go to the last, yeah.
This is the one where I want to come to, where you say you have the 5G, you have these requirements, and these are the outer kinds are the bullets where you would say this is what IETF is currently doing, right? Most of them, and this is also what you have to fulfill to get 5G, right? If you think multipass TCP is here, ad hoc is here, network coding is a group, machine learning is now starting. Mobile Edge Cloud, MFV, SDN is the combination over here, network slicing. So all these things are currently, we're discussing this already, but if you form them together, this is what we call the 5G atom, right?
Okay.
So I think you will hear about this, and I think we are at the right place here with 5G, just to understand how we relate to all of the individual groups. Well, thank you very much.
Okay, thanks, friends. Thank you. So, Tom is here. We're going to go quick, and then I think we wanted to have some Q&A, but I guess we'll leave it to the end, okay? Yeah, I have it here. We don't need your laptop. Yeah. And I need the... Is here?
That was mine. You had your own one, right?
No, there's only one.
No, this one? Or you mean the presenter?
Yeah, no, the USB.
No,
USB.
It's in there.
Oh, it's there. I need the USB because that's the control. USB, okay. Now you can do that only with this. Okay. Now it should be okay.
Okay, great. Hi, my name is Tom Herbert, and today I'll be presenting ILA for 5G. This is some work that Julius Miller from AT&T, myself have been kind of starting. So I presented a little bit last time. I think we had the Boston, Buenos Aires on the 5G book. And I'll give a little more detail, specifically how ILA might be applied to 5G. So just a quick recap, ILA is an identifier locator kind of protocol. We split IPv6 address into locator identifier. The upper 64 bits are routable. These are essentially identify each physical host. The low order 64 bits form the identifier. This is kind of like the virtual or logical address. So, given that we have the 500 billion target, actually, I was thinking IPv6 is a really good fit for that.
How do you deal with the collisions for the identifier?
So we'll get.
Oh, we'll get to
to
that. Okay.
So there's obviously a lot of management and control plane behind this.
Okay.
So the components. So one nice thing about ILA can run on end hosts and devices, or it can run the network. One important thing, obviously, is a mapping database. So this is mapping identifiers, which again are like the local or logical address, to the physical address of devices. So in order for a network like this to work, we have to distribute this mapping table. Conceptually, the full size of the table is up to the number of objects, which can, so we're thinking about ways to scale this into the 500 billion or trillion range. And then there's a control plane behind all of this, which distributes the mapping. And this is somewhat like a routing protocol. There's actually some initial efforts for doing things like this in BGP, but we tend to believe it's more of a very large-scale distributed database. We'll have some probably some more work to do on that.
So again, sorry, this mapping database, isn't that DNS?
It's not DNS. It's live DNS. It's mapping one 64-bit number to another, essentially. So it's a database lookup. One of the things we're looking at, and I believe we're going to start at least a mailing list on this, is something called hyperscale address management. To basically tackle this problem. We believe it's a generic problem. We've already seen this in the context of NVO3, where we're trying to map virtual addresses to physical addresses. But in the larger context for object mapping instead of just VMs, scale goes up a lot. As we see the 500 billion number. I should mention that in Facebook we are intending to deploy ILA, and this is kind of the overview of it. Fundamentally, it's fairly simple. A source sends a packet, does a DNS lookup usually, gets an address, and doesn't know this address other than it's a normal IPv6 address, sends it on to the network. And somewhere in the network, we can actually translate this basically virtual address into a physical address by overriding the first 64 bits with a locator. So in this way, we send packets untranslated. They eventually hit what we call an ILA router that does the translation, and that sends it on to the actual physical destination where the node with that identifier lives. And one of the optimizations we can make actually is if the host device supports ILA, we can have some sort of redirect-like mechanism, resolution protocol sent back to the host and try to eliminate the triangular routing. So there's some optimization we can build into it. Looking at kind of some of the other solutions or concepts specific to 5G, I would say there's a few advantages of ILA. So one is there's no encapsulation involved. If you send 64 byte IP packet, IPv6 packet, in ILA it's translated as a 64 byte IPv6 packet. The network will see this. If it's a TCP packet, it sees the TCP over IP packet, which means it can do all of the normal network optimizations, hardware offload, and things like that. Also, since there's no encapsulation, we eliminate a lot of the headaches of encapsulation, trying to figure out MTU issues, dealing with UDP checksum, other tunneling things. Another advantage is there are no changes to the transport layer. This is really a difference with ILMP, which is actually kind of the basis of ILA. ILMP requires some changes all the way up into the transport layer, which really makes it hard to deploy on the host, and then on a router, I'm not sure what they do. I guess they have some sort of proxy. And then the other thing is, this is also transparent to the application, which is nice. Okay? So one of the nice things we want in the mobile case is make the application as transparent as possible to the network and vice versa, I guess. We also have an open source implementation. So this, the basics of the ILA host have been upstream Linux for a while. And we also had a hackathon last Saturday and Sunday. And the Cisco guys brought up an ILA router over BGP. which is really cool. And I actually have an intern right now working on an ILA router in XDP, which is another high performance data pack. So the upshot of that is we believe we can implement an ILA router in commodity servers, commodity hardware, basically pretty efficiently. So we think we can get several hundred million packets per second going through a normal server doing ILA. So it's not to say that we don't want hardware support, but we can deploy without hardware support, at least in the initial rounds. So looking at the requirements specific to mobility, 5G, we want to consider homogeneous versus heterogeneous handoff when you cross networks, IP addresses changing, things like that. A single user device being mobile versus a whole network. So the cruise ship analogy, when the cruise ship moves, whole networks change location. In the network, where would ILA run? So we actually have several options here. First option is basically run it between the border router to the internet and gateway somewhere in the middle of the network. And then ILA would occur between the border routers in blue or between different gateways. Those would be doing the physical routing. And then beyond that, the base stations and the user devices would see normal packets. In the spirit of efficiency, latency, at some point we want to push that closer to the user device, closer to the edge. So for example, in this case, two user devices could talk just through the base station to each other. The base station does the ILA translations and handles that, or you can talk between base stations. And of course, we always want to be able to talk from the user device all the way to the internet or external networks, in which case the ILA really occurs at the edge. So in the middle of the network, you would see ILA addresses. At the edges, you would see the untranslated kind of global addresses.
Sure, 2 minutes.
And as I mentioned, we do have the ability to push this into the host. My concern with mobile, obviously, is this does require modifications to like the OS, Android, what have you. It's very possible, and it becomes a nice optimization, especially in a multi-home host, which obviously most mobile devices are going to be anyway. So in terms of control plane, kind of to answer your question, identifiers are allocated globally. Within Facebook, we have a mechanism to basically allocate unique identifiers using a timestamp. So it would kind of depend on the use case. We do believe there will be some hierarchy allocation. So for instance, if two providers were participating in this, each of them could have one component of the 64-bit namespace. Then they can allocate identifiers within that space as they wish. Now these identifiers are compatible with two different providers, so they could participate in ILA, and we can actually, that's where we get into the heterogeneous handling. There's some more detail that mostly Julius did, I guess more specific to some of the 5G architectures. And pertaining to the model of 5G, we also want to consider when we do move the applications into the network. I think this is the ultimate goal: make the service model closer to the actual devices, get down to that 1 millisecond latency. In this case, we could have the application servers that can participate directly.
Any newcomers? Yeah. Okay. Yes. Yeah. Thanks, Tom. So we go to the next. The next talk is Peter. Next talk is Peter. Okay, just close this. And yours is PowerPoint. This one. Yeah. Okay.
All right, thanks. So normally this kind of subject takes about an hour and a half with questions. I've tried to distill it down to 10 minutes, so it's ought to be kind of interesting. We'll start with just the whys and whats of slicing. The first presenter talked quite well about all of the different permutations and combinations of the air interfaces and why that requires different air interfaces to support them all. But essentially, you can think of it as different QoS, different QoE requirements for many different types of needs. We've got IoT devices, which require low bandwidth and almost a connectionless type interface. And then smartphones, of course, with very high bandwidth. There are the delay reliability requirements, which you saw in some of those first videos, and you can imagine extending that out into a real automotive environment. It's a little scary. But then you've also got issues like very fast mobility, and by mobility I mean DVDT, right? I don't mean in terms of IP mobility, I mean in terms of the speed at which something is moving. And the current OFDM technologies which are used with 4G today don't work at high mobility speeds. But if you want something that works at high mobility speeds, it's not necessarily efficient for things which are moving slowly. So you end up needing multiple different OFDM technologies. So you end up with requiring different OFDM technologies for different spectral bands that are used simultaneously. And this leads you to the concept of slicing of the area interface right from the get-go. So the slicing requirement comes from the problems and challenges of chopping up that area interface and using it for multiple different UEs with multiple different QoSs. There are lots of other interesting issues around being able to create networks quickly and migration and so forth. Another way to think about what slicing is, you can look at it from the UE, right, the end user device perspective. So if you group UEs by space, capacity, coverage, QoS, delay, administrative domain, those form a set. That set can be thought of as a slice. Those UEs are part of that slice. Now, in terms of the network, and what does it mean from the network perspective, I thought long and hard about different ways of describing this, and the easiest thing I can come up with for folks like yourselves is to think of it as a set of subsets of the resources. I'll explain that in a minute. But that set of subsets forms a new set, which essentially becomes an end-to-end network. So from the UE's perspective, there are 3 or 4 different ways you can slice a UE. Right? Each UE can be in its own independent slice. That's pretty obvious, pretty easy. I can come vertically through the UE and have essentially different virtual machines inside the UE. So the radio access technology presents itself to an individual OS. That OS sees one interface. Those apps see one OS. It's like having logical UEs within one physical UE. More interesting, I can chop it horizontally, where these different radio access technologies that are supported by the UE at the same time present themselves as multiple interfaces to a single OS, and the applications then have access to different QoSs within the single UE. And of course, you can get into complicated combinations and permutations of these two. So they're slicing from a UE perspective. Now, from a network perspective, it gets a lot more sophisticated, a lot more complicated. The way I'm describing this is that a slice is a subset, a set of subsets. So the universe of all the resources that I have available to chop up to slice starts with the antennas, the analog front haul that connects to those antennas, and then these 3 sets in the middle here represent the digital signal processing, which is essentially driving those antennas. So this is the hardware, the CPU and hardware resources that drive the antennas, fabric which interconnects that hardware and compute resources. And then here we refer to the numerology, the mathematics, or the digital signal processing, which is actually implementing OFDM or other technologies at the antennas. So from here out, it's sort of an analog interface. From here back, we then have the backhaul, so packet interfaces. So this could be a data center fabric, it could be a core network, transport network, etc. And then we have the actual core network, the packet processing portion of the 5G network or the 4G network, which is essentially NFV. It's the implementation of all of the servers, all of the resources, and so forth. And then a slice can be thought of as taking a set of these subsets. So some of the antennas, some of the front haul, some of the digital signal processing fabric resources and numerology, some of the backhaul, and some of the data center resources for the core. And you do not have to have a proper subset, right? This can be, you can use the complete set if you want to for a slice, which leads you to an interesting diagram which shows you that here I've got 4 different slices, red, blue, green, and yellow slice, that they're sharing resources up to the point where There's a fork in the resources here for different radio access technologies. Perhaps the red slice is using a different type of OFDM with different spacing between the subcarriers, which are better for high-speed mobility, and maybe the others require a more normal OFDM. And then we're splitting here at the EPC, so I'm using different core processing. Maybe one of these is a traditional IP core, and maybe one of the others is list-based or one of the non-traditional IP cores. So you have the possibility of running and splitting at different points. And I can split into two different further slices after I finish the core processing, because I might have different content that I wish to provide or different downstream processing. So the slicing can be thought of not only in terms of the physical resources, but the logical partitioning that happens downstream. So you're almost forming these trees, slice like trees. Once you have this ability to create slices, then the obvious question is that I probably want to be able to move resources from slice to slice. And again, this starts with the driving requirement at the input, which is that I want to move spectrum from one slice to another. Right? So at a particular point in time, one of my slices is going to use some amount of capacity, and later on in the day I wish to switch the resources to a different slice. I need to be able to move and reassign that spectrum on the fly. If I reassign the spectrum, then things happen downstream. I need more capacity downstream to do the digital signal processing. I need more capacity downstream to do the packet processing, and I may need more capacity downstream for the interconnect. This all has to be make before break. Right? We know how to do make before break here in the NFV space, with virtual machine movement and so forth. We know how to do make before break in the transport and packet space. We've been doing that. But what happens all the way back to the front end of the system? All right, so just to quickly go through some of the areas that are potentially impacted or impact 5G, vice versa. Obviously, the addressing growth is an interesting concern. Information-centric networking and LISP are very interesting topics because they potentially require a change in the UE. And that's always been an impediment for some of these new technologies. With slicing, there will be the possibility of changes in the UE, and there will be the possibility to run brand new technologies experimentally, or even to migrate them from experimental into something interesting and worldwide through the slicing technology. So slicing technology is an interesting way to adopt these new and interesting evolutions.
I think you're going on time anyway.
Yeah.
Let me show.
Okay.
2 minutes.
Now you just distracted me.
Sorry.
And so there's also the possibility, like I said, of using these technologies internally to the next generation cores as alternatives to mobility. So there's sort of two interesting use cases for ICN, LISP, et cetera, in this space. And I apologize if I'm taking a whole lot of people's work and lumping it into one. The GTP, of course, could potentially be extended. The function chains, because the next generation packet core, and in fact the enhanced packet core of 5G today, is implemented, or will be implemented, virtualized within a cloud interconnect downstream of those core components to load balancers and firewalls and so forth, is a perfect application for SFC. I2RS forces and other SDN related technologies are highly relevant because some of the packet core functionality is essentially virtual routing. And the virtual routers should be split into a set of virtual control planes and a set of virtual forwarding planes. And you need to communicate, of course, between the virtual control plane and the virtual forwarding plane. And the ideal way to do that is one of these technologies.
I guess time's up.
Time's up?
Yeah.
Anyway, multiple other technologies. Probably another one of great interest is multipath TCP, because as I said on my first or second slide where we showed the UE with multiple slices, multipath TCP is an ideal way to use those two interfaces, and it's entirely likely that 5G radio access technology is going to support multi-connectivity for higher bandwidth. So, and of course Yang and everything else.
Yeah. Okay, thanks, Peter. Next is Dino. Dino's talk is here. Oh, he's going to show it. Oh, I don't know if I have enough USB
All I need,
USB space
all I need is this.
because here you only need one.
All I need is this.
Oh, you need to connect to
That's it.
your iPhone. Oh man. Okay. Everybody, please, if we don't have blue sheet, we have white sheet. If you didn't write your name, please write here. Sorry? Is it up? Mediacom? Okay,
Go.
that's fine.
Okay, so I'm going to present list BID mobility, and it turns out that most of the list mobility features are across 3 internet drafts, and the authors of all 3 internet drafts are listed right there. So I'm going to have a longer version. This is going to also be presented in the list working group Thursday afternoon. So if you want to hear the longer version, please come to that. And also, I'm doing a Pecha Kucha presentation on Thursday night at 10:30 p.m. Sorry it's so late, but it's going to describe the last 10 years of Lisp. It's kind of, Lisp is turning 10 in the fall, so it's going to describe the entire chronology of Lisp. So I'm going to explain in this presentation why Lisp solves the mobility problem, and I'm going to explain that there's actually 2 forms of separation in use locator ID separation, and that we also have an optimization called where we can do handoffs at near 0 packet loss. So I can continue with that, or does the audience want to see a 1 minute, 1 slide presentation of Lisp? Yes or no?
Yes.
Yes, okay. Because there's some, oops, that should have happened.
You can't use remote control.
I can, but this is supposed to be a hyperlink. Okay.
Okay.
Okay, so the bottom part is Lisp has a data plane. And basically, host systems are assigned EIDs, which are just regular IP v4, v6 addresses. There's no special syntax. They send packets, host A to host B sends to each other. And then there's these Lisp XTRs that encapsulate packets and send them over the internet and to their RLOs. And the RLOs are addresses that are routed in the core routing system. To be able to get the mapping from host B goes through RLOC Y, you go to a mapping database system, which we had many various proposals on how to do it. The API to the mapping system says that the ATR, the encapsulator, sends a map request to the map resolver. It finds where the registered EID is through the mapping system. The map request can be forwarded to the ETR to be responded back, or he could proxy reply, allows the ITR to cache the mapping, and then he encapsulates all packets after that. That's it in a nutshell.
I can
No,
I
not
can
now.
do it for you.
No, I can go myself.
Okay.
now. Okay, there's really only 3 ways to solve the mobility problem. And if anybody tells you there's a 4th way, it probably fits in one of these 3 categories. If something's going to be moving around and you don't want to use any locator ID separation mechanisms, you either have to use mobile IP, where you have to inject the moving entity into the routing system. I'm going to explain each 3 of those mechanisms. Okay, host routes. Pretty much, it's been experimented over the last 20 years. It's pretty much a non-starter. If I'm an IP address and I want to move around and I inject it in the routing system, that single host route for this single entity that's moving has to be injected everywhere in the routing system. That's going to cause handoff problems, too much state, and there's also policy restrictions where the host routes can't get everywhere you want them to get, where you wanted them to get to. And if you're multi-homed, now I have multiple addresses, so it adds to the state problem and the latency. So it's pretty much a non-starter. So we have the notion of home. If I have an IP address and it's attached to a subnet, that means it's part of the topology somewhere in the internet. Why is that useful? If I'm moving around, I really don't have a home, kind of nomadic, right? So conventional wisdom says that if I have a home address, that my packets are always going to have to go home, and that home agent has to find a foreign agent to send packets to you. Conventional wisdom says doing triangle routing has latency. Why even start there? We want the shortest path between any 2 points for communication, regardless of their moving. Okay. Now, how does multi-homing work with multiple homes? What if I have 2 IP addresses and one's at my physical residential home and one's at my work, and I want to use both of them? Do I now have to route packets to both homes, one or the other? It gets confusing. We want to be multi-home. Most devices have multiple radios, so we're going to need to support that. And when you roam, you may roam to a high bandwidth area, but your home location has worse bandwidth, so you're going to be affected. Why can't you take advantage of the higher bandwidth place that you roam to? So the notion of home and assigning an address that's something associated with home is probably not a good way to solve the mobility problem. Locator ID separation really is the only solution, because what's moving is something that's fixed that never changes, which is called in Lisp endpoint ID. Endpoint ID is always fixed to that thing that's moving. And what you do is you reattach to the network by getting a new binding to a routing locator. Okay? The moving entity has a single address. That makes things very easy for debugging. Even though you're attached to multiple radios, you can have multiple RLOCs in an RLOC set that the single EID maps to. That's the way to solve the problem. And you always get the shortest paths between RLOCs. Low latency. So we have 2 forms of separation in Lisp. The EID and the RLOC set can be co-located in the same moving entity. That's documented in the Lisp mobile node draft. And the EID is a moving entity, and the RLOC is a stationary network-wide, which means the EID moves, does not support Lisp, and the RLOC that discovers the EID does support Lisp, and that's in the EID mobility draft. So one example of that is maybe a virtual machine in a data center has an EID, and it moves from one data center to the other. The RLOC that it changes from is one top of rack switch to another top of rack switch. So this is an example where Lisp is running on the UE. It's assigned an EID maybe to its loopback address, and it retrieves these RLOCs through DHCPs from these different providers. This is what's documented in Lisp mobile node. This is not necessarily what we're recommending. The Lisp working group is recommending for the 5G solution. We want fast deployment. Even though Peter said we could support it using slicing, that's something we maybe could experiment with. But we probably want to use this solution. This is what the EID mobility draft says. The EID is the UE, but the RLOCs are actually in the network. So maybe an access point for Wi-Fi, maybe a B or an S gateway in the 5G world.
Okay. 2 minutes.
2 minutes. Okay, so if you want to know the details of these drafts, I'll go into detail at the Lisp working group, so I'm just going to fast forward to the most important part. So this is the 3rd draft that does make before break. This is going to cause near zero packet loss for handoffs. And we call them predictive RLOCs. If you know the direction you're going in, you have the ITR that's encapsulating packets, send it to all of them. And rather than finding the moving entity, the packets are going to be wherever the moving entity may go. So it's going to be dropped everywhere except for the place it's currently at. If you want more information on predictive RLOCs, we're giving a presentation on that in the Lisp working group.
Okay.
I'll go back one.
Okay.
Okay, so basically, how does Lisp fit on the current 5G or proposed 3GPP architecture? Now, if you look at this slide, there's a lot here. This is existing non-Lisp sites, branch offices, data centers, where you see these double colored things. This is where Lisp can run. So those are Lisp sites over there, a branch with Lisp, a data center with Lisp. And now we can look at all the possible combinations of where you could put Lisp. Okay, so first and foremost, today Lisp is running in these environments where a CPE router is encapsulating to a top-of-rack switch, and so this internet does not have to carry the EID addresses of each of the cores. Okay, so the first thing we could do is we could put Lisp here and do encapsulation between the S gateway and the P gateway. That would be good. And then what you get is whenever a UE moves, UE is signed an EID, it's an IP address, can be v4 or v6. One question that has to be answered with 5G is, are you going to explicitly not support IPv4? Very important question. But anyways, if a UE moves from this S gateway to that S gateway, then a new binding is done, so the P gateway knows to encapsulate there versus there. Okay, so that would be a good solution. Another solution is put it closer to the moving EID. So then you get much more granular mobility domains where if the EID moves from one node to another, you could have it done there. In both cases where the decap happens at the P gateway, it could re-encap to maybe a branch router that it's talking to. Maybe this phone is talking to something at a branch. This guy encapsulates, he decapsulates the packet from here, re-encapsulates here. This would be called an RTR function, re-encapsulating tunnel router. That could be done. Probably the best solution is to keep it close to the moving entities so you have good granularity, and that he encapsulates all the way to where he has to go. This is supporting an overlay where the functions are in the network as close as it can to the edges of the network, but not in the edges. Yeah, there's no reason why that top of rack switch that's doing the decapsulation can't be in a VM on a server somewhere in the data center. But I think since it's a network function, let's save the CPU resources in the UEs and in the servers for doing applications, and let's put Lisp in these various things. So I want to, when we have the time, I want to entertain thoughts on where people think the best place to put it is. But you can see that there's a lot of flexibility there. We really want Lisp to be able to go from this point to that point so it can support all the various traffic flows.
Is Michael here? Oh, here, okay. So we're gonna have to,
Yeah, I'm all done.
yeah. There is another Lisp talk, so just hang around. And Michael Mant, okay, Michael? Thank you. And we need the, where is USB? Yeah, it's in here. Oh no. Where is the USB that comes with it? Somebody took it, I guess. Not intentional, maybe. Where is it? Then I'm gonna have to control. USB that comes with this? Anybody has?
I usually just work.
Yeah, I know, it was here some. Anyway, well, go ahead, Michael. Yeah, I'll change it from here. You show it.
I'd like to talk about the global locator, local locator, and identifier split. It's microphone, please.
Microphone, yeah.
This is slightly different. Does this work? Yeah, you hear me? This is also locator identifier split, but it's a little bit a different flavor than Lisp and ILA. And the application in a 5G context is probably pretty much the same. That's why I will concentrate on the differences. This is work that was discussed about, say, 8 years ago in the research routing group, and it was published some years ago in the Future Internet Journal. So next slide, please.
Sure.
Here's the overview. We have an IPv6 internet backbone. We have some local domains. And the idea of GLI split is that we have a routing locator that is specific to a local domain, and which is the local locator, and a routing locator that is specific to the global routing domain. And within the local routing domain, we use addresses that are composed of the local locator and the identifier. And within the global routing domain, we are using an address that is composed of the identifier and the global locator. That's the main idea. And the attachment point between the local routing domain and the global routing domain are so-called GLI gateways. This is very similar to the other approaches like an ITR or so, ingress tunnel router. We have interworking concepts with classic IPv6 domain, and within a GLI domain, we may use classic IPv6 nodes and upgraded GLI IPv6 nodes. Next slide, please.
Actually, I think you can change it with this, yeah. I realize that VSV is already there.
Okay.
And you can use those as a pointer.
Okay. So some nomenclature. We have the identifier, we have a local locator, and the identifier is used to look up the local locator in a local mapping service. The global locator can be looked up using the identifier in a global mapping service. So this is the address structure. We have 3 different types of addresses. We have identifier addresses that contain only the identifier, and they may be used for lookups. We have local addresses that consist of a local locator and the identifier that is used for local routing. And we have the global address that is composed of global locator and the identifier. So this allows us to have attachment points within a local routing domain that are independently recorded in the addresses. So we can change the attachment point in a local routing domain without changing without changing the global address of the device. Okay, so how does this work then? Within a local network, we have node 1 and node 2. Node 1 wants to communicate with node 2, so it looks up the local locator and pushes this local locator on onto the packet header, and this packet can be used for forwarding. In a global routing context, this works similarly. So node 1 wants to communicate with node 2. It looks up in the local mapping service, the local locator for node 2, but it cannot find it. So it queries the global mapping service and finds the global locator for this destination node. This packet is forwarded through the GLI gateway. The GLI gateway substitutes the local locator of the sender by its global locator. That packet is forwarded to the destination, and yeah, that's about it. So we need this GLI gateway to hide any local structure from the outside world. And this is address rewriting mechanism, which is stateless. So this is the big difference to NAT. Okay. We have quite a bit of flexibility with this GLI domain approach, with this GLI approach, because we can use different paths, and this is all transparent to the end nodes. There are also interworking mechanism between classic IPv6 domains and GLI domains. And here is the summary. With GLI split, which is very similar to ILA and to Lisp, it is possible to change providers without internal renumbering. What is the difference or the commonality, the similarities to Lisp? In Lisp, we use encapsulation, and in classic Lisp, the identifier and the local locator was kind of intermingled. In ILA, there is the global locator and the local locator combined in the locator part of the address. And here we have 2 different addresses used for it, the local address and the global address. So it's just a different approach. The benefits are very similar because of the locator identifier split approach, Multi-homing is facilitated even for smallest GLI domains. It can be exploited for multipath forwarding, in addition to traffic engineering, improved reliability, and mobility support. GLI split is incrementally deployable on a per domain basis and also within a single domain. The migration from non-upgraded GLI nodes to upgraded GLI nodes can be done gradually. So, yeah. We demonstrate the incremental deployability of GLI split by means of a proof of concept implementation in Omnet++. GLI gateways perform simple address rewriting without the need for session state. This also holds for interworking with classic IPv6 internet. In contrast to many other proposals, GLI split does not need triangle routing via EXO devices for interworking with the classic IPv6 internet. The full set of benefits is available only for communication among GLI nodes with upgraded network stacks, but GLI split provides also advantages for upgraded GLI nodes when communicating with the classic IPv6 internet and even for classic IPv6 nodes in GLI domains.
Okay.
So,
Yeah.
that's it.
Thanks. Yeah, you finished even on time, even earlier. Yeah. So which leaves us a couple of minutes for discussion. You can go to the mic or just stand up, and if you want to ask questions to Mike or Michael or anybody else, we have a couple of minutes for discussion.
The main point I want to make is locate identifier split is a very attractive mechanism, but there are various approaches to do it.
Yeah.
Hi, just a quick question about the global mapping. In any talk of Lisp and ICN or these other next generation data planes, it's always about the data plane, and there's not a whole lot of talk about how the global mapping works. Seems to me that's the Achilles heel.
Say again, please.
Could you talk about the global mapping, or do you know? I mean, I think you understood.
We do not require a specific mapping system. We could use any
but
system.
You need at
that
least
is all
one. There needs to be at least one that works on a global scale.
I mean, in the Lisp working group, DNS-like systems are proposed. What's the name of the DDT, for instance, and we also presented some years ago firms as a mapping system. So there's even an overview paper about different mapping systems. But this is not very specific to the actual locate identifier split approach.
Yeah, no, I realize it's sort of orthogonal. It's just, it seems to me it's the Achilles heel. It's the part that you know, the miracle happens box.
Yeah, it's a mapping system. It must be very powerful. It must be reliable. It must be secure.
Yeah.
Yeah. But it's a different problem.
It's somebody else's I mean, it literally is the miracle happens problem, right?
Mhm.
Assuming this, then all this other great stuff happens. But how does that work? Right?
Well, there are, you know.
Well, that seems to be the theme of all the overlay stuff that's been going on the last 5 years. Everybody wants to argue over the data planes. And then they say control plane has to scale, has to be robust, magic goes here, and somebody else is going to worry about the magic. So over the last 10 years, we've been working on Lisp. We've had 5 or 6 different ways of doing the mapping system. And we've concluded we want to use DDT, which is a DNS-like approach. It does not use a DNS protocol. All it uses is the iterative lookup procedure from DNS. We can give a presentation on that, a deep dive on that anytime you would like. Okay.
It is GDP,
DDT,
global.
delegated database table.
Oh, okay.
Hi, Tom Herbert. So I think my question is going to be a little more general. So we had, great presentations today. I think the use case for 5G is pretty impressive. Yeah, it's going to be if it materializes, definitely a very large scale network, unlike anything we've ever seen. Yada yada yada. That's great. Simple question: where do we go from here? So, will this become? Are we going to have a BOF? Soul or
okay. Yeah, that's a good question.
Yeah.
Now, we appreciate that you wrote the draft about your presentation, and there was some discussion, but you didn't give replies to those questions, by the way. Also, please, everybody do their homework, write drafts and submit. You can submit anywhere, but I mean, write anything, but if you submit draft your name and then 5G, ANIP or something,
Right.
that's even
But are
better.
we submitting drafts to a working group? It doesn't seem like
It's-
we are, right?
No, I mean, you can write something else, but you
Well,
can
we
write
write drafts all day
our group
long.
name also. But you announced a draft name, right? And somebody commented, Dirk commented, I think, but you didn't reply, yeah. So we need discussions on the mailing list.
Yeah.
So actually, yeah, right now, maybe this year we're going to continue presentations like this because we have not yet explored all the 5G space. But next year, hopefully, we want to, scope it. Maybe ILMP is one good area to scope. These related issues, another area to scope, and so on. So then go for a BOF, yeah.
So will we have a BOF next IETF or? are you thinking later?
No, I think next
Okay.
year, not next IETF. I don't think so. I mean, we would like to have it if if you're ready, if you have drafts.
Well,
Yes.
so the date I've heard for 5G is 2020, and if you do the math,
Yeah,
there's a lot of work to do. So,
yeah, we still have
yeah,
time.
obviously, that's pretty ambitious.
Two areas we have not even touched upon is IoT for 5G. The other one is vehicular 5G. I think Professor Vitek mentioned a little bit. So those are issues. Maybe next meeting we can have some presentations, and then we continue more of these current things we have and so on. Okay.
Yeah, I'd like to restate Tom's question. When is 5GANG IP going to be a working group? Because until it's a working group, other standards bodies won't take this work seriously. So my question is, even higher level maybe than Tom's, is when will 3GPP take this work seriously?
Yes, that's a good. We have GSMA person here. She can say something.
I am not the 3GPP spokesperson. Hi, Natasha Rooney, GSMA. I did speak with some people about this work, and the message I received was that everything below IP they were dealing with in 3GPP, and IP upwards they felt like should be dealt here. I don't know if that's going to make people feel warm and fuzzy inside or not. I did want to come to Mike for another reason. I actually just don't know what this group wants to do. All the presentations are great and all very relevant pieces of work. I'd actually like to see a draft charter, even if it's a crap version, just a draft charter to know what the group wants
Go for
to
above.
do. Yeah, well, not even just go for above. Like, let's just put some stuff down on a piece of paper,
Make some charter.
and then we can argue about it on the list, and then we can see if it's worth doing. With summer being where it is, you probably are not going to have a BOF next time, or at least not a working group forming one, because I don't think anyone's going to approve it. But you could aim for March, and I think that's probably a better time frame. So I think you're right about that. But let's start arguing about a charter, because there's enough people here. So yeah.
Thanks, Natasha. We'll do that. Okay.
So, Dan Romashkanu,
We might be kicked out of here. Yeah, go ahead.
Right.
Done.
before being kicked out, just my observation, it's from the presentation and the draft that I have read right now, I'm not sure that I know if I'm to write a charter or if I am to do a BOF actually exactly where it would belong. Because I have seen like disparated pieces of work, then may belong in routing, may belong in the internet area. Some of them may be actually incremental work to existing working groups. So there is still much work to do, and I believe that Backchat is perfectly right. We need to actually do show activity on the mailing list, write drafts, and especially comment and answer comments in order to kind of help crystallize our layer the ideas here and understand where we can add value in the ITF.
Absolutely. Thank you.
Yeah.
Laurent, go ahead.
Lionel Moore. Yeah, two short comments. It's if you want to do something for 5G, it's not time for slideshow presentation. It's a time for defining what you want to do or what it is needed to do within IETF and to define the scope of the work. Because 3GPP will not wait for 2 years to have any solution. They're already working on they are closing the architecture work, and even we have a pre-work on pre-5G work.
SA2 work, yeah, we are very
No, but
familiar.
we have also protocol
SA3?
SA3 for security, but for the protocol aspects in city level, we have already some work ongoing on separation between the control plane and
Yeah,
service.
we are following closely what's going on in 3GPP.
Yeah.
Of course, it's very
So
important.
the point is that if you are not coming up with in a short time with a charter and a concrete work plan, I think all this discussion will be useless because 3GPP will not wait for any solution.
So you're saying we should hurry up?
Yeah,
Absolutely. So then do like Dan said.
yeah. You can sum up it like that.
Do like Dan said. Okay. I guess that's it. Folks, thank you to all the presenters. Great presentations. And those who didn't write their names, please write your name.